Okay, let's start the second talk. So the speaker is Scott Baldridge from Louisiana State University. He will talk about a new geometry for multitudes, not magnitudes. Please welcome.
Thank you. So I just want to thank you for the hospitality. When I told my daughter that I was going to Korea, she got very excited. So this is very important that I take lots of pictures, and so far it's been wonderful. Hospitality's been wonderful. Okay, so today I'm going to talk about basically it should be a talk in which like a colloquium talk. Everybody should be with me for at least half the slides, and I only want to make basically 3 points. And one of them is a warning, so that'll be the first point. The second one is an observation. And when you see the observation, you go, why didn't other people make this observation? And then the third point is justification. So I make an observation, and I want to justify why it would be useful to look at this, use this observation. Okay? So let's get started. So the first point is, it's kind of a warning. And there's a little bit of history behind this, and so I want to talk about the history. So Aristotle said quantity is either discrete, in other words, a multitude, or it's continuous, a magnitude. And I want to focus on, so discrete, like that's combinatorics. So there's a wealth of, but I'm not talking about combinatorics per se. I'm talking about discrete in terms of geometry, in terms of a smooth n manifold. So you take a smooth 2 manifold, and what can you do discretely about it? So the guiding questions for geometry is we have a canonical geometry for magnitudes. In other words, lengths. We're going to calculate lengths on our manifold. We're going to find the distance from point A to point B. So what is the corresponding geometry for multitudes? And the warning is, as you'll see, when I talk a little bit about the history, we got really excited about this, and we forgot that. Or at least we've downplayed that part. And I want to lift that back up. So just a little bit of the history, what got us interested in measurement using lengths when we're talking about smooth manifolds. And there's actually quite a bit of history here where you think about the top mathematicians of the last 500 years thought really, really hard about this. So I'm going to throw a couple of things up on the slides here, and I invite you to go explore some of these papers because they're fantastic. So, for example, Holder, in 1901, he axiomizes what a magnitude is as an ordered additive structure supporting the measurement by ratios. Now, that didn't come out of nowhere. That came, we're talking at this time is Dedekind cuts and things like that. That's in the same time period. But that didn't come from there either. It originally comes from Newton. Newton talked about defining numbers as basically ratios between different lengths. And you pick a unit, and then you know what 1, 2, 3, 4, and so on. So in hindsight, he talks about a measurement space, and at the same, it's really a one-dimensional real vector space with a fixed unit. So that's really, but I want to give you some sense of vector spaces. Well, vector spaces were then new. They were only kind of fully worked out at pianos in 1888 as for the axioms of vector spaces. Now, we know that there were people that were studying things like this before. You can look at people like Hamilton and the quaternions and so on. But in terms of the axiomatics, this was all kind of fresh. new. And that is the thing that we really kind of held on to. We really went after this, and we held this tightly. So magnitudes became native to smooth manifolds because we have these nice, beautiful R-linear structures on them. This is the R-linear of the one-dimensional real vector space. Okay, so obviously, well, before we get to where that led us to, I just want to say, when I say that there's really fantastic mathematicians who thought about this hard, another person is Whitney, Hassler Whitney, of basically any type of mathematics. If you look far enough back in it, there's Whitney smiling at you. And if you go back in terms of what quantities are, he thought very hard about it. Wrote 2 papers on quantities. I encourage you all to go look at those papers. They're very interesting in terms of philosophy. He gives a rigorous formulation as a one-dimensional. He again brings up one-dimensional real vector spaces. It really becomes this notion about one-dimensional real vector spaces. But he goes way beyond, because what he wants to do is define rigorously what a centimeter is. A centimeter is, and then a mathematical definition. Does it make sense? And it's captured by Holder, but he wants to go further. So what's interesting about Whitney is he defines the square root of a centimeter. He can find out. That's not take the square root of something and times a centimeter. He's literally saying you can define the square root of a centimeter. So if you take the product of a square root centimeter and a square root centimeter, you actually get a centimeter. This is what I'm talking about. And he needed this because he wanted to define units for the square root of joules divided by kilograms. What does that mean mathematically? And he comes up with, it's not as easy as you'd hope. But he does show you how to build any kind of rational root of any unit that you'd like in terms of building dimensional analysis. But always, so that's fascinating. Always, he's talking about it's always continuous. It's always a magnitude. It's not a multitude. And the magnitude's always based on our R, which is good. I'm not saying it's bad. I love Riemannian geometry. That's a favorite subject of mine. But I'm saying that we got excited about it. We went down that road, and then we forgot that there was this other road that was proposed by Aristotle 2,000 some years ago. So when we talk about manifolds, you knew I was going to bring up Riemann. Yes?
Why is starting with joules rather than starting with meters?
Because just simply because it comes up in calculations you do in physics. Like there's reasons for why you would look at starting places where, obviously when you take the square root of joules divided by kilograms, you take the square root of that, you're going to get speed, velocity. But that's not the point. The point is that he wants a rigorous definition that he can start with, and then when you take the square root, you have a way of defining it.
So it's easier to rigorously define mass and energy first.
These are fun. Yeah, these are fundamental.
Oh, I was just going to say square root of joules over kilograms. That's just meters.
Yeah, that's just. So, okay, so here's an example, a very simple one. That's an example of a compound unit. So, can you show me? Here's a good exercise outside of today's talk. Here's 5 feet. Sorry, my snaps aren't good. That's 2 seconds. So 5 feet, 2 seconds. Show me how to divide 5 feet by 2 seconds. Now we say that it's 2.5 feet per second. But why? Well, the reason why is because in 7th grade, your 7th grade teacher said that that was true. And Whitney says, no, 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 no. We don't get to say that's true. We need to have some method of explaining this mathematically. And he's working up based off of Holder. Holder's working out based off of Newton. Newton's thinking in terms of Aristotle. Like, there is a long chain of thinking that's happening here. So are we good? Of course, we're going to talk about Riemann because that's the structure we pick for magnitudes. It's the most basic one. There are many geometries on smooth manifolds. We have symplectic forms, complex structures, G structures, connections to gauge fields. We've seen some of these throughout a couple days. But if you want to measure magnitudes in the Aristotelian sense, you want to use a Riemannian metric. And then, of course, once you've chosen your Riemannian metric, then you can measure in lengths and angles. For example, here's the length of a path, your manifold. So so it's not that the Riemannian metric gives you a metric space. That's not the initial thing you get. You get a section of the tensor product of the tangent bundle, cotangent bundle. But then you can use that information, that structure, to then define a length. So the length is something that's a derivative of the structure you've chosen. And the question I have is, what would that be for a multitude? So my warning is, let's be careful. My warning is, maybe we've gone too far down the distance of length, because it's great and it's wonderful, and no question, should always be studying Riemannian geometry. But there's this other option. Aristotle says there's another option. We've talked about multitudes. What would be that structure? And it can't, yes?
So why do you consider geometry of multitudes? Why do you want to consider multitudes?
I'll show you. That'll get into the second part, or third part. It's my justification. Okay, so a multitude, we're going to pick a structure, and then the structure is going to give me, like a metric, is going to give me information about multitudes versus magnitudes. Discrete, some sort of discrete. And for multitudes, we want, for multitudes, we want a structure that extracts counting type data. Discrete. And the philosophy of the talk is, you knew this was going to be what we're going to play with. We only have triangle. We're going to use triangulations. And we're going to use Pachner moves. Okay? So triangulations, and these are a natural carrier for multitudes. So fix a closed smooth n manifold, then so I'm starting with a smooth n manifold. You get into all the, is topology, is top equal to smooth and all that. Start with smooth. And then a triangulation lets you count simplices and find combinatorial patterns. Many deep invariants are naturally described by triangulations. So state sums, spin networks, TQFT partitions, Triavero. They're based, the way that you start calculating these are pick a triangulation. But triangulation itself is not canonical. You picked one, but so what? So the question is, what should be the same? And this is my observation. So before we make the observation, let's talk about Pachner. Pachner's theorem says that two triangulations of the same PLN manifold are related by a sequence of Pachner moves. So if you have one triangulation, you have another triangulation, you can get from one to the other via basically these simple local moves. So let's do an example. So in dimension 2, you're going to like this. A 1-3 move replaces one triangle with 3 triangles. Let's pick a vertex in the center of your simplex, and then cone. A 2-2 move in dimension 2 is take two triangles and replace them with two triangles. Does that look familiar? I think we've had some talks on this. So, so you have the 1-3 and the 2-2. In dimension 3, it's the same thing. I'm not going to try to draw this. This takes forever to draw. You take a vertex. Sorry, I keep doing that. Take a vertex, put it inside, and then cone, and you'll get 4 new tetrahedrons. And so that's a 1-4. And if you have 2 tetrahedron joined along a face, you can remove the face, connect the top and the bottom with an edge, and get 3 new tetrahedron. So you replace 2 tetrahedron with 3 tetrahedron. Now, if you're into smooth manifolds, this is great. So I've just given you a way to, if you can come up with an invariant under both of these moves, you've got an invariant of a smooth 3 manifold. And it seems kind of like every other type of move that you make for 3, like if you do Haggard diagrams, you've got the diagram, and then you have the stabilization of the move, and you have the, and this is the stabilization type move. And so you can kind of see that they're related. You can keep doing this. So in dimension 4, you have a 1-5 move. You have a 2-4 move and a 3-3 move. Dimension 5, you have a 1-6 move. 2, they add up to 3, 4, and so on.
Any number of roots are not allowed in any dimension because there's a constraint of the number.
Right. So in this case, right, like this 1-5 move is you take a 4-dimensional simplex, pick a vertex in the middle, cone on it, and you'll get 5 new simplexes. And if you have 2 of them together, much like this, you can replace them by 4. You can go back and forth. Yes? Yeah. Well, what's nice about these moves is they're local. So you're only working with those 2 simplices, and you replace them by 4, and you will have a triangulation afterwards.
No, I mean, these moves can be thought as a reading of the boundary of one dimensional higher.
Yes. Yes, exactly. So if you don't know anything about Pachner moves, that's another thing I'd recommend going and looking at. They're a lot of fun. Here's the point. So here's my observation. In any dimension n, a 1 to n plus 1 Pachner move is a stellar subdivision. It's just what I said. Insert a vertex, cone. And you can do an n plus 1 if you just see it. You can remove that vertex. These moves refine and coarsen without changing the local combinatorial information too much. Too much. It keeps it pretty much the same. So my observation is make an equivalence class on that. If you do that, take try M to be the class of suitable triangulations of M. Suitable meaning, you know, the cone, the link of any vertex is a nice sphere, and there's no weird triangle identifications on your triangulation, but generally nice. And you say one triangulation is equivalent to another triangulation if you can get from one to the other by just one n plus 1 Pachner moves. Okay? So back here, this would be this group. I'm saying two triangulations are equivalent if and only if they're in this set, that set of combinatorics. Okay. This is not all the Partner moves. We are always excluding the middle. And the intuition is, sorry, do that again. The intuition is we're modding out by the controlled notion of local refinement. That's the key. So I'll explain why more in a second. Let's just say a couple words more about Partner. They're completely local. So if you start with a triangle, you can do a 1-3 Partner on that triangle and and then you can do it again. And notice you can start here. You don't have to do it on every one of them. You can just move around locally. You could do barycentric, but it's by definition it's not local. So if you do this first barycentric subdivision right here, then if you had a triangle right below it, then you say, well, that's not a triangle anymore, so I'm going to have to do something like that. But that's not a barycentric subdivision of the original triangle, so, oops, sorry. So then I'm going to have to do this. Okay, but now I've got two new vertices I've created. I'm going to have to do barycentric subdivisions on those triangles. Those are going to cause me to do barycentric subdivisions on those triangles, and you have to go do them on every single triangle in your triangulation. So it's not local. And worse yet, barycentric subdivisions kind of all tower up to be the same subdivision. So what's really nice about Partner is that you're just staying local the entire time. So this is my first theorem, my first definition. You like that picture of me? See, it was me before my wife kissed me. So, so an arithmic K on M is the equivalence class. Just take the equivalence class of that equivalence of n plus 1. On suitable triangulations of M under these n plus 1 Partner moves. So it's different, right? I'm not asking for, like if you ask, like in the two-dimensional case, if I said, I want an invariant that's invariant under 1-3 Partner move and 2-2 Partner move for a two-dimensional closed-oriented surface, then I've got an invariant of that surface. What's the only invariant you're going to pick up? Closed-oriented, smooth surface. It's not a wild question. Thank you. Yeah, you're just going to get the genus. You're not going to get anything interesting. What I'm doing is I'm going to go after invariants of kappa. And now it can be very interesting because it's no longer, like I'm not requiring it to be the same under a 2-2 Partner move. The 2-2 might change the invariant. Does that make sense? So this has given me multitude geometry for a chosen M. And it's exactly, I called it an arithmic because it's like a metric, right? I was really, really, really boring. I just went and looked at the Greek word for like a number. And you know, if you want to say like a length, it's like metric. And if you want to like a number, it's arithmic. And so a representative triangulation of, if you have a class and you take a representation of it, you're just picking up a triangulation in that class. It feels like a gauge choice for me as a physicist. And then if I start switching inside that class, then I'm making different types of local refinements. So let A of M be the set of those. So that's my observation. That's it. That's the observation. Why don't we just look at this class instead? And it has lots of nice things that remind you of metrics. So if you choose kappa on M, that's like choosing G on M. In other words, G doesn't give you length initially, you derive length from it, lengths in the manifold after you've picked one. Gives you continuous magnitudes. This gives you discrete multitudes because it is, by definition, a combinatorial object. You worry about paths in the space of metrics. If you're a gauge theorist like me, that's what you worry about. And if you're in arithmic geometry, you worry about discrete moves in AM. Those discrete moves are obvious, right? Like for a two-dimensional arithmic, you're talking about doing the 2-2 Potner moves. So to go from one class to another, you replace 2-2 with these two triangles with those two triangles. And then you might ask, well, what happens if I go around a pentagon? Maybe I start talking about cluster algebras. So that would be a set of discrete moves in this space and worthy of study, as we've seen already this week. You derive curvature invariance of G, and from here you get quantum invariance. You get quantum invariance of the arithmic. So metrics organize the magnitudes, the arithmics organize the multitudes.
So, why did we, in the discrete side, we have the quantile control? It's already, this means already quantized?
No. Let me show it to you. I'll show you a version of a state system. So you're absolutely asking a question that I'll answer later. Yeah, the 1 n plus 1 is special. And the reason why is imagine, and this is really key. So you're asking a great question. So what happens when you take a metric G and a almost complex structure J, and they happen to be compatible? You get a new type of geometry called a symplectic geometry. You see that? So the beautiful thing about an arithmic is that eventually you want, I'm not talking about it today, but in essence, you want to be able to take a metric and an arithmic and say when they're compatible. And when they're compatible means that if you take the limit of refinements going to infinity, yeah, then it becomes, you get a smooth, you start to get an approximation via the triangulations of your smooth manifold. So you can imagine, I'm not going to talk about it today, but that's the idea. Let me say one sentence in a, yeah, go ahead.
Isn't that also very nice? You have some notion of duality, right?
Yeah, there's dual. Yeah. Okay, so I didn't talk about this. It's like if you do a 2-3, it's dual to a 3-2. So you have the 1 and n plus 1 and the n plus 1 and 1, and then they're duals to each other. So yeah, so my point is that the 1 n plus 1, if you just keep subdividing every single simplex and keep doing a 1 n plus 1 n plus 1 move, and you get a new branch, and then you do it again, the vertices will start to become dense in the space of your manifold. And now that's really important in terms of doing geometry, the Riemannian geometry type. Okay. So the actual first arithmic invariant is the Euler class, but that's kind of dumb. Right? For a surface, right? If you compute the vertices minus the number of edges plus the number of faces, you get an arithmic invariant, but it's the same on every class. So it's not dumb because it's giving you a smooth invariant, but what I want is something that's specific to the arithmic. So the first kind of non-trivial arithmic invariant on a smooth surface is something called the Penrose polynomial. So let me talk a little bit about Sir Roger Penrose. So so I'm going to use a trivalent graph, take a small neighborhood of a trivalent cellularly embedded graph. So most people call these ribbon graphs or fat graphs, but they're trivalent. And you carve out, so you take a little neighborhood, and then for each edge, you put a marking. And then what you do is you build a state system. So this is all Penrose. Doesn't that look familiar? In every circle that shows up, you replace it by n. So that's, by the way, if this looks like a Kaufman bracket, Kaufman once told me that it's kind of in the air. So this is 1971, Kaufman was the 80s, right? And people were thinking about these relationships, and this was one of the first examples. I would dare to say, go read Penrose's 1971 paper, and what you're going to get is a class in modern mathematics, and you realize, oh my gosh, all the mathematics we love and play around with actually is kind of initiated in that paper. You can see, for example, Triavero invariants, and it's all there. Okay, and in fact, he was thinking about it from a physics perspective. And the physics perspective is he's looking at intertwiners, and it's really a fundamental representations of SU3 coming in, and then you get the kind of dual fundamental representation going out. And if you flip that, you get basically 3 tensor 3 tensor 3. So he was playing around with the tensor calculus. And I point that out because maybe you have your favorite that's not SU3. So go play. Go play, have some fun. Maybe you'll find an arithmic invariant. Okay, before we go too much further, why a trivalent graph? And a trivalent graph is not, if you have a trivalent graph, what I'm going to actually do is take the dual. And if you take the dual graph is I guess I should have taken that and put it there. There. So I'm going to apply Penrose not to the triangulation, but I'm going to apply it to the dual of the triangulation, which will be a trivalent graph. Okay? And if I do that, I need to know what the 1-3 Pachner move looks like. So the 1-3 Pachner move is, well, I'll take the dual here. So the dual is just a, oops. Dual is just a blow up. All right, you take your original vertex and you replace it by a cycle, a 3 cycle. Not too hard. But now I know what I need to search for a invariant that's invariant under that move. So this is me after my wife kissed me. And me 20, 30 years ago. Made me much younger. So a beautiful calculation that you can do, is not very hard, is to calculate that the Penrose polynomial at n of the blow-up is n minus 2 times the original. So here's the observation. Observation is that 1 over n minus 2 times the number of vertices divided by 2. I make that normalized Penrose polynomial. Now it doesn't matter how many blowups you do. In other words, it is an invariant of that class. Yeah, given any two triangulations in my original kappa, then those Penrose polynomials, normalized Penrose polynomials, are equivalent. And therefore, just define the kappa Penrose polynomial based on any one of them. And then last year, normalized Penrose polynomial is an invariant of an arithmic. But it's just an observation, really. Hmm?
Is it the universal? Is it the universal?
Universal.
Complete.
Complete. Oh, well, I don't know. Like, you have to remember that this is now on a surface. So yeah. So this is picking up something about all CW structures or all triangulations of a surface. And as you move from one triangulation to a different triangulation, it may change the invariant. So I don't think it's a universal invariant. I think there's other invariants of kappa classes on two-dimensional triangulations. I don't have any reason not to believe. In other words, go have fun. Like I hope that this after this lecture you go and you try out your favorite invariant and see if you have a kappa invariant. This is one variable. You can think of the Penrose, by the way, it's not wrong to think of the Penrose polynomial as kind of like the pre-Jones polynomial or the Jones polynomial of a surface with a CW structure. Yes.
N equal 1, maybe?
No. Doesn't show up. Yeah, I think that we're looking at quantum information here. And I'll show you why. Yeah, it's the number of circles that happen when you I'll show you an example. You can see an example. Okay, so let me say a couple more words here. It's highly non-trivial. So if you take the kappa to be just two triangles glued along their boundary, that's the dumbest triangulation of a sphere you can make. Its invariant is n times n minus 2, or n minus 1. But now that works for any triangulation. So here's another triangulation of this two-sphere that's equivalent to that original triangulation. And if you go through all the work to compute it, you'll get n times n minus 1.
N equal 2 is Euler characteristic.
No, because well, yeah, yes, here, yes, but there's a lot of mistakes that you can easily get into because you're looking at a very simple triangulation. So yes. In fact, all the space of arithmics, right, is going to include every planar graph, every trivalent planar graph. So it's huge. And if you calculate those, you're not going to, there's no guarantee that when you plug in n equal to 2, it'll be 2. Maybe. I've never tried that, but I doubt it. Okay, from a physics point of view, this is you're basically building a tensor network. This is why Penrose was thinking about it. And you can think of it as a partition function, a vacuum amplitude. And more importantly, what's really important about this is that the full Tut, Balabash, Reardon, and transition polynomials, these kind of basic polynomials that you would use in graph theory, none of them are refinement invariants. They don't behave well under refinement. So they turn out to be not kappa invariants. So Penrose polynomial evaluated at n is the Euler characteristic of a filtered n color homology. So let me talk about that. Fair enough? This is the part that's going to get fun for all of you like Ivanov homology. I can make it work. Okay, this is my picture of Mikhail. I ran all these pictures through AI, and I didn't want to upload a picture of a living mathematician who maybe didn't want to be. But we also have him here in the audience, so it's if you want, you can go look at him. All right, so there's a deeper package, and that is filtered n-color homologies. And it's a graded filtered kappa invariant. If you have to work harder, much harder. But these behave like curvatures for arithmics. They're richer than just the polynomial. So when you take when you find out what polynomial of you have your Penrose polynomial, not the normalized version. Plug in 3. It'll tell you the Euler characteristic of the filtered 3-color homology. And colors are important here because it encodes the colorings of the graphs. The n means something in terms of coloring, like in graph theory. The n stands for the number of colors you're going to use. Okay? It's built out of obviously. This is screaming to let's build a hypercube. Let's see if there's a way to categorify that. Let's see if we can show that there's a differential. And that's exactly what I did. So here's an example of a theta graph. And I drew it out as a hypercube because why not? And you see that it looks a lot like Mikhail's type of hypercube, but it's a little different, right? Yeah. This has got 3 circles. This has got 2 circles, 2 circles, 2 circles, 1 circle. And then if you look here, it's got 1 circle. So it's not behaving like a knot because you have something going from the same number of circles to the same number of circles. And that throws a monkey wrench into all sorts of mathematics if you were to think of it like a knot. But if you stop thinking of it like a knot, huh? Oh, that's the name of the homology. So I'll show you how to build the homology. All right, so doing exactly the categorification, you replace all the circles with vector spaces, and you replace all the edges with maps, and you want those maps to behave well. So that looks like this. So for the 3 circles that were here, replace it by v tensor v tensor v, or v hat. There were 2 circles in this column, so they're v hat tensor v hat, a v hat, and a v hat. And obviously, if you're going from 3 circles to 2 circles, you're looking at a multiplication in your TQFT. But then you have this weird eta that's happening when you go from 1 to 1. All right. And then you say, well, take the direct sum of these going down, direct sum of these going down, direct sum of these going down. Call that your chain complex. Call the sum of these maps del hat and del hat. And then you hope that you can set this up so that del hat is 0, and that's true. That means you have a homology theory. Okay? How much time do I have? Oh, you got plenty of time. All right. So that's just this slide. It's just saying that you take the direct sum of your v hats. This is the interesting part about this slide. So in Mikhail's theory, you pick a ground ring, you join X, and you mod out by X squared. Or if you get more fancy, you can higher end. So this would actually be like Havana homology, if you got rid of that. This is actually more like Lie homology, which is another Korean mathematician. I'm working at this level, so I actually proved it for that. And then I did a lot of work calculating the spectral sequences and calculating E-infinity pages, because I wanted to see what the Lie homology would look like, the equivalent of Lie homology. And then I realized, after doing a lot of really hard calculations, that I was just looking at the colors. The color. Yes.
If you replace 1 by Q, it's the
Yeah, it's just. Yes. If you, yes. CPN. Yeah. And you can do all that. That's in the paper. I'm actually, when I'm talking about the filtered n-color homology, I'm talking about the Lie homology-like object. So after you've taken the E-infinity page of your spectral sequence. Okay? So this is the part that I could have several talks on just that. But imagine that it's there, and you pick a different type of basis on this, C0 through Cn minus 1, and those become your colors. You can think of those as coloring the different faces of your surface. And what you're doing is those maps actually will compute for you the number of colorings of those of the surfaces in your hypercube. Yeah. You don't get that in the Q graded though. If you're just working in Q grading, Havana-like homology, that's a much richer invariant, right? Like we all know Barnatan's famous quote, right? That Lie homology was very uninteresting for a knot, which makes it very interesting. Remember this? And it turns out that the Lie-like homology here is very, very interesting. So let's talk about that. So yeah, that's the color basis. Here's the actual maps. It's actually a 2 plus 1 TQFT. I could go into all of how that works. Turns out that del squared is 0, del hat squared is 0, which allows us to get a homology. That homology is filtered n-color homology. So that's the definition up there. And this is me and my co-author, Ben. I had to get a picture of Ben for the following reason. Look at him. He's probably the rarest type of mathematician you can find, which is a cowboy. Yeah. So if you ever see Ben, if you ever invite Ben to give a talk, he'll come looking very much like an American cowboy. Okay. I'm just a standard American. It's kind of cool. All right, so the dimension of CH hat is the sum of all proper n-face colorings of the dual state graphs on the ith column. So this is a little trick, right? If you take a triangulation, take its dual, it's a trivalent graph, and then I'm finding the colors on that trivalent graph. Okay? That colors of the n-face colorings on the dual correspond to vertex colorings on the original graph, triangulation. So in particular, in the 0th column, the dual is in fact itself, or the triangulation is itself the original triangulation, and the dual is that. So let me just point that out to you. If you took a theta graph, that's these circles literally represent the faces of the theta graph. So in that 0 column, it's actually computing for you this. So it's computing the number of that first column is computing the n color the number of n vertex colorings of your triangulation. So this is the last part, and then I'll wrap it up. So what did I do? I gave you the warning. I pointed out the observation. Observation is we should concentrate on 1 n plus 1. There are invariants of it, famous invariants. Now I need to justify why you should care about that. And I've come up with a thing that looks very much like Mikhail's theory for knots. And it's that thing that we're computing for knots, the thing that's like the thing that we're computing for knots is computing something very important about the graph. In other words, the colorings. And the way you can express that is say, well, the 4-color theorem is true if and only if this is not 0 for all nice triangulations. In other words, all triangulations that don't, when you take their duals, don't have bridges. So do you see the space, just in the space of 2 dimensions, the space of arithmics, literally you should think has every possible type of planar graph as kind of a core fundamental piece of that arithmic class. And you're going to get different coloring counts for every single one of them. This is why I said probably doesn't correspond to. Okay. This theorem, you say, like when I figured this out, I said, yay, I can prove the 4-color theorem. And then I found I couldn't. Because what did I just do? Does everybody see what I just did? I took a really, really hard problem in mathematics, and I just shifted it over and replaced it by another really, really hard problem in mathematics. So, oh well. And a lot of the way, that's what a lot of the recent theorems about gauge theory and 4-color theorem have done. They take a really hard problem, like Kronheimer, Mrozka, beautiful, beautiful, beautiful stuff. But that's still a really hard problem to try to solve before you get the 4-color theorem. Okay, but in the last year, we have the following. So this is my last slide. So Ben and I proved that there is a new route to the 4-color theorem. And I could actually eventually prove it. And if I wanted to go through the 633, the 4-color theorem breaks up into 633 easy to solve cases, right, that use computers. And if I wanted to do that, I could run my software on each of those cases and reprove the 4-color theorem using a completely different method than the way that the graph theorists do it. But I could. So we did that with a new proof of the Birkhoff diamond showing that it was reducible. And the Birkhoff diamond is the original configuration that started the entire process that led to Appel-Hawkins' proof of the 4-color theorem. If I wanted to, the beautiful thing about the Birkhoff diamond proof that we gave is that we didn't use a Kemp chain, which is absolutely necessary in Birkhoff's theorem. So the very thing that you need to use, we can do without it. Which means that there's likely that with some work, we can actually do it with smaller configurations. So the Birkhoff diamond is basically 5 pentagons globbed together. And that's the smallest configuration that you have to use. If you do 3 configurations, you can cut the 633 by 25%. Because the three pentagons glommed together shows up as pieces of all those other configurations. But you need to use the Kemp chain. Well, we now have a way of doing it without the Kemp chain. So this is a new path. This is a new idea. And if I wanted to, I could do all 633. I want to actually prove the 3 pentagon is reducible. Or the 2 pentagon, or the single pentagon. That would be Kemp's original proof. Another thing that we did with Luke Hoffman this year is we broke Spencer Brown's statement that he had proven the 4-color theorem without using a computer. So back in the 70s and 80s, he was walking around telling everybody that he had found a proof of the 4-color theorem that didn't involve using a computer. And he got really upset when people didn't believe him. And part of the reason why it was like a not even wrong statement, you know, like you didn't know if it was right or wrong. So he got to claim that his entire life. And we found a counterexample. And the way we found the counterexample is by having this new technology. This is what led us to figure out, whoa, this is how we should look for things that do this. And that counterexample is by no means easy. That counterexample is you have to do 60 hard calculations and you hope that you come back to the original coloring. And so that's by no means a simple defined problem or simple defined example. But it went on, people didn't know. You didn't know if you could find an example like that. So that took 45 years. And then last year, we also came up with the first example of a calculation of the original Penrose at a pentagon. And that took 55 years. And that uses technology that's very much like you see Bar-Natan. It is very much a Bar-Natan kind of calculation. So the point is that, we finish with this, there are these invariants. They behave extremely well. These type of invariants behave extremely well under the 1-3 Pochner moves. And from them, you can build invariants of the kappa invariants. And then those kappa invariants, because in the class, you can take that to infinity, means that you can actually get you can get a kappa invariant sitting inside there that's a smooth, almost like a very nice approximation of your original manifold. Now just do this for 3 manifolds. And if you think like that, you're thinking like me. With that, I'll end. So thank you.